Hey, fellow mathematicians! Welcome to the podcast where math is figure-outable. I'm Pam.
And I'm Kim.
And we make the case that mathematizing is not about mimicking steps or rote memorizing facts, but it's about thinking and reasoning, about creating and using mental relationships. We take the strong stance that not only are algorithms not particularly helpful in teaching, but that mimicking algorithms actually keeps students from being the mathematicians they can be. We answer the question, if not algorithms and step-by-step procedures, then what?
So last week we had a fantastic division challenge for the world, right? So much fun.
Oh my gosh, that was fun.
So we decided that we're going to tackle a little bit of division today.
I mean, we are not done with division because let's be clear, there's a lot. Like division is interesting and it's complicated and it's complex, lots of ins and outs and therefore even more fun, right? Like we can really have a lot.
Super figure-outable.
Super figure-outable, not rote memorizable. Nicely said. Okay, so we're going to be a little transparent here and say that sometimes when we do the podcast, we plan it out a little bit more, and I will actually tell Kim the problem that I'm about to give her so she can think through it a little bit. We've done that. We've also done it where we've literally thrown out the problem, and neither of us have done a lot of thinking. That's not true. I think I've always thought about it at least a little bit, or if you've given me the problem, you've thought about it. But the other person hasn't heard it. Today is the cold case where I've created some division stuff and Kim has not heard these before. So this will be a little fun and exciting. And here we go. All right.
Totally willing. All right.
Hey, Kim, if we were going on a field trip and we had 500 students, so it's a whole school's going on a field trip. Mm-hmm. And we decided or maybe it's field day. I don't know. Give me a good context. Maybe it's field day. Because for whatever reason, we need water bottles and we were taking stock of what we have. And we've got a bunch of water bottles and we know that right now for those 500 students, we have 250 water bottles. And I'm curious how many water bottles each of those students could have.
Okay, cool. So I grabbed my pencil and paper just in case. But 500 kids, 250 water bottles. We don't have enough water bottles for everybody.
So how many water bottles is there per kid?
1/2 of a water bottle per kid.
Like that's not very good, right? We can only give them half of a water bottle per kid. So that's okay. So it gets even worse, Kim, because we don't have enough. But what if I had 1,000 students and still we only had those 250 water bottles? How many water bottles would each kid get?
So then everybody would just get 1/4 of a water bottle. We have twice as many kids, but the water bottles stay the same. So they're going to get half as much.
So it's kind of like before they had half a water bottle each, and now they get half as much of that, and half of a half is a fourth. Is that a way to think about that?
Yep. Mm-hmm.
Okay. Let's go back to our 500 students. So we got those 500 students. What if the situation gets even worse and we only have 125 water bottles? We miscounted. We only have 125 water bottles.
Okay. So same number of kids.
Mm-hmm. 500. Yeah.
500 kids. And when they were 500 kids and 250 water bottles, they got half a water bottle. So now there are half as many water bottles as before. So they get half as much water as they got before. So instead of getting 1/4, now they get 1/8. Oh, they got a half before. So sorry. They were going to get a half of a water bottle when they had 250 water bottles, but now you have half as many water bottles. So they get half as much water. So they get 1/4.
Half of a half is a fourth.
Right. Mm-hmm.
Okay, cool. Okay. Let's see. What if I had our same 500 students and 250 water bottles? That was what we sort of started with, right?
Right. And that was, they got a half a water bottle each.
Yeah. What if we had 250 students and the 125 water bottles? How much?
Half a water bottle per student.
How do you know?
Because I know 125 is half of 250.
Yeah. So we had the original 500.
Oh, you mean so we have half as many students, but they get half as much water. So they're still going to get a half each.
Okay, cool. What if we had 50 students?
Oh. Okay.
So we had 500 students got 250 water bottles, and then you said 250 students would get 125 water bottles. Wait. How much water did they get for?
When there were 250 students and there
Uh-huh.
were 125 water bottles, they each got half a water bottle.
Did you say a fourth? No, I
Did
don't
I say a
remember.
fourth? They get a half because they get the same as when there were 500 students
How do you
and
know that it's the
250
same?
water bottles. Because there's half as many students and half as much water. So what they get is the same.
Ah, that seems important.
Yeah.
Is that always true? If you have half as many students and half as much water, they get the same amount of water?
As the earlier scenario, yes.
Would that be true if you doubled the number of students and doubled the water? Would they still get
Mm-hmm.
the same amount of water?
Mm-hmm.
Okay. So let's see. For 250 students got 125 water bottles, they each got half a water bottle. What if I had 50 students get 25 water bottles?
They're still going to get half
How do you
because,
know?
and actually, I'm writing on my paper, and I wish you could see. This is kind of a thing, but I wrote 500 students, line 200, so over positionally over
Mm-hmm.
500 students for 250 water bottles, and I actually wrote equivalent or equal to 250 students with 125 water bottles.
Okay.
And then
So
I wrote 50 students to 25 water bottles. And you found a fifth as many students, and it's a fifth as many water bottles. So that's going to be the same again.
So like from the 250, a fifth of 250 is 50. So
Yeah.
fifth the
So I
number of
wrote divided by
students.
5.
And then from the 125 water bottles, a fifth of the 125 water bottles gave you 25 water
25.
bottles. So a
Uh-huh.
fifth the number of students get a fifth of the water. They still
Have the
getting
same.
the same amount of water per student.
Mm-hmm.
Could you do that from the 500? Sort of our original, we had 500 students,
Oh yeah, that might
250
even be
water
easier
bottles.
because you have a tenth as many students and 1/10 as much water.
Because 500 to 50 is a tenth,
Yep.
and 250 to 25 is a tenth.
Mm-hmm.
Okay, so what if I had only 10 students and 5 water bottles?
They'd still get a half of a water bottle each.
I mean, to me, when I look at those numbers, 10 to 5, it sort of screams a half.
Yeah.
And
Yeah.
kind of
I would
50
have
to
liked that
20.
problem first, please.
Like if I would have said the ratio of students to water bottles is 10 to 5, you could have said, oh, they're getting a half a water bottle
Yeah.
each.
Yep.
At which point you would have said, not enough water, Pam, hydrate more. But you could have then sort of worked up and said, well, if we had 10 students and they got 5 water bottles, then 50 to 25. In fact, when I say that now, you almost could sort of look at some of these and almost see the half screaming. I wonder how many people,
Yeah.
when you heard these numbers, didn't hear the scale and you were hearing the halves sort of screaming like 500
Yeah.
to 250, 250 to 125, 50 to 25, and 10 to 5. Sort of that half just kind of screams out the whole time.
Yeah.
That's kind of interesting.
Yeah.
Why are we doing this? So there's a strategy that if I can think about scaling the number of students and scaling the number of water bottles with the same scale factor, then I end up with an equivalent ratio of students to water. And that can be helpful when I have other random problems. So, for example, Kim, another random problem. What if I asked you 244 divided by 16? Like if I had 244 students and 16 water bottles. I don't know. That's probably not the best. This is probably not the best context to begin with at
Yeah.
all.
Yeah.
I probably should have come up with a better context. Sorry, everyone.
Yeah.
But what are you thinking
It's
about?
okay.
Is there something
Well,
you could
like
do?
at first glance, I'm glad that we just talked about this strategy, to be perfectly honest with you, because 244 divided by 16 is kind of yucky. But my palms are sweating a little bit. And here's the thing, like I feel very comfortable taking as much time as I need. And if we need to pause, then we're just going to pause. But there is something to doing math on demand that I like. I want to make sure that I'm explaining my thinking well enough that people can follow.
I mean, you're on a
that's the issue.
podcast. That's, it's a little
Yeah.
crazy.
Okay. So,
Yeah,
all
yeah.
right. So I'm going to think about an equivalent problem that might be nicer. So I'm going to scale those down, divided by 2.
So if you have half as many
whatevers. So that's going to give me 122 to 8. 122 divided by 8.
Okay, because half of 244 is 122, and
Right.
half of 16 is 8.
Right. I think I can do that again. I love that they're both divisible by 2 again. So I'm going to divide those both by 2 again, which is nice. I can half those numbers really easily. Oh, I like that. I like that a lot. Because now I have 61 divided by 4. So half of 122 was 61. And half of 8 was 4. So now I've scaled down a couple of times, and I'm left with the problem 61 divided by 4. Does that make sense?
Yep.
Okay. And I love that I know 60 divided by 4 is 15. And 1 divided by 4 is a 4th. So at that point, I kind of changed my strategy a little bit, because I recognize 61 divided by 4 is 60 divided by 4 plus 1 divided by 4. And so that gives me 15 and 1/4.
Cool. So you're saying you could actually use this strategy of finding equivalent ratios to solve a division problem.
Love it.
Huh. Wow.
Yep.
Hey, I wonder, is that helpful in any way in a problem like, random, how about 432 divided by 5?
Oh.
How are you going to scale those down, Kim?
Eesh. Oh, you know what? I don't want to scale down, because I don't, I think it's going to leave me with something odd. But what I am going to do is scale up.
What?
Yep.
You mean if you had twice as many water bottles for twice as many students, they would still get the same amount of water?
Yep. And so that I'm going to scale up. I'm going to double the number of water bottles and double the number of students.
Random. Okay. I don't know where
you're going,
Kim.
Because then that gives me 864 divided by 10, which is 86 and 4/10.
Or 86.4, because you know this thing about divided by 10.
Yep.
Because division by 10 is so brilliant, and you have a lot of numeracy, and you recognize that division by 5, if you scale it up to division by 10, bam! Like anything divided by 10, you can just sort of like think about that pattern of multiplying and dividing by 10 in our number system. And 864 divided by 10 becomes 864. I totally just repeated what you did. Sorry, but
it's great.
Made me happy to like cement it in my own head. Hey, I wonder if you could do something similar, listeners, if you were to think about, and this whole time we should have been saying, as soon as we give the problem, pause the podcast, solve it on your own. Retroactively, hey, when you hear a problem, pause the podcast, solve it on your own, and then listen to what Kim's doing. So do that on this last problem. How about 61 divided by 2.5? Or 61 divided by 2.5, or 61 divided by 2 5/10. How would you solve that problem? So pause. All right, Kim, what do you got?
Okay, I'm going to scale up again, because scaling down when it's divided by 2.5 doesn't feel like it's going to be super helpful. So I'm going to double both of those numbers and create the problem 122 divided by 5.
Because double 61 is 122. Double 2.5 is 5. Okay.
And then I don't love that, but I'm going to scale up again. I'm going to double 122 to get 244, and double the 5 to get 10. So now I have created the problem 244 divided by 10, which is 24.4.
Bam!
I like. Thanks for giving me problems that I like.
You're welcome.
Well, which really they're not, right? Those problems, like, they're not. It's not like you gave me super nice ones. It's just that we have a good strategy that make them.
Yeah, and so if we parse that out a little bit, we've developed a strategy that if I have a division problem, I can think about that as a ratio of the these new words, of the dividend to the divisor. Did I do that right? Yes, of the dividend to the divisor. I can think about that ratio. And then I can find equivalent ratios that might be a problem easier to solve.
Yep.
And often it's not. But when it is, then I might as well use it. And if I get, I'm tell a brief story. Y'all, I was a high school math teacher. I was an expert in teaching with graphing calculators. I was doing a workshop. I remember the day I was in San Antonio, Texas, and I was working with a group of teachers, and we had a rational function. So we had like variables on the top of the fraction or the rational expression, and variables in the denominator. And I remember I had this graphical way of looking at it. We're going to do this really cool stuff on the graphing calculator. And one of the participants said, well, yeah, but you could just scale both of them, and then the denominator will be so much easier to work with. And it was kind of when we were actually figuring out a particular point. And so we had numbers at that point, not just variables. And I remember looking at that person going, whatever, weirdo, that's like really, that is this weird trick that you just pulled out of a hat. And I don't do tricks. I just do, I do mathematics, not tricks. And it's because I didn't have any numeracy. But I remember the moment going, I have no idea what you just did. Y'all, let's free up the world to know that these relationships exist. Once we know they exist, then we can play with them. We can experience them. We can build relationships so that when we reach a division problem, we have choices.
Right.
Like all of these problems we could have thought about quotatively. We could have thought about how many of the divisors were in the dividends. But instead, kind of like when, Kim, when you solved 61 divided by 4, you kind of thought about how many 4s are in 60 and how many 4s are in 1 to sort of think about 61 divided by 4. That's a quotative strategy. But we can also think about it partitively, where, again, you think about it as a ratio, and then you can find equivalent ratios to solve the problem, the easier problem once you've found an equivalent ratio. Bam! Like those are important relationships that we need in division so that we can all think and reason more multiplicatively about division, which leads then into all sorts of success with fractions, decimals, and percents, all those rational number things, which then leads to more success in higher math. Ba-dum-dum. And I love it. That's like one of my favorite things to do ever. Thanks for playing live math with Pam on the podcast today. Kim, that was fantastic. If y'all like what you just heard, if you're interested to know more about division, we just created the Building Powerful Division workshop, and it has launched, and we are thrilled to offer it to the world, where you can learn not only how to divide yourself like we just did, but how to teach powerful division to your students. Yay, verily, even powerful polynomial division. So we have a little bit of an extra bit in the workshop for those of you that teach higher math that want to know how all of this applies to thinking and reasoning about polynomial division. Not just division with whole numbers and decimals and fractions and all the things. So if you want to check that out, mathisfigureoutable.com, more and more in-depth content workshops coming out day by day. Not really, but at least semester by semester as we try to get more workshops out, K-12, for more teachers to learn to teach more and more real math. So, if you want to learn more mathematics and refine your math teaching so that you and students are mathematizing more and more, then join the Math is Figureoutable movement and help us spread the word that math is figureoutable.